Hi everybody, it's Mrs. T coming to you from home as we work from home during this coronavirus pandemic. I hope that everybody is healthy and doing well. I received a question yesterday regarding going over the Maxwell Boltzmann distribution and a couple of different things about it. So that's what this video plans to do for you. I had originally planned to do my extra helps as a live stream, but because of logistics, that's just doesn't seem to be the best case because of the fact that there would be a delay after the live stream between when it was live and when it posted to YouTube. So I just decided to make this video in advance. It will post at regular extra help time, and that's what I plan to do each week. So keep sending me questions either by remind or email, and I will prepare videos to go over those in case anyone else has the same question. You're welcome to reach out with any questions that you have. Let me know, and I will be more than happy to help you. For anyone who doesn't know me, I'm Elizabeth Tuminello. I'm a chemistry teacher at Sanford H. Calhoun High School in Merrick, and this is posted on my YouTube channel, Mrs. T Chem Talk. On that channel, I do have a lot of other chemistry videos if you want to look and peruse. So the first thing about the Maxwell Boltzmann distribution, which should look similar to what you've seen before on the picture, temperature measures average kinetic energy, and that means that not all molecules possess the same amount of kinetic energy, and not all molecules are moving at the same speed or velocity. Remember that kinetic energy and speed are two different things, but the average kinetic energy is just the average of that amount of energy that the molecules possess. The speed is also related not only to the temperature, but also related to the molecular mass. Remember that molecules that are heavier or lighter will move at different speeds, but at the same temperature, they will have the same average kinetic energy. We also know that since this is an average for the kinetic energy, we see this curve. And because we are in the coronavirus pandemic right now in 2020 here, this may look really familiar to you because we've been talking about flattening the curve and flattening the curve. And that's not the same thing that's going on here in the Maxwell Boltzmann distribution, but the images should look similar. What we have here is that we have the relative amount of molecules and then the speed over here on the x-axis. And this curve shows us that the most prevalent molecules is right here. And underneath the curve here, we have the area here that tells us the amount of molecules. So as we change the temperature, we don't change the amount of molecules, but we will change this distribution of how many molecules have what kinetic energy. So as I said before, gas samples that are at the same temperature will have the same average kinetic energy, but the molecular mass will influence the speed or the velocity. At the same temperature, heavier molecules move slower on average, and lighter molecules move faster on average, even though they both have the same average kinetic energy. In class, we discussed trying to throw a bowling ball versus trying to throw a softball using the same amount of energy. If you propel a bowling ball with the same amount of energy as you propel a softball and you're throwing it across the room, you will be able to throw the softball at a faster speed. You will be able to achieve a faster velocity because of the fact that it's lighter. That's a simplified analogy. So again, I said for the same number of molecules at the same temperature, each gas will have the same average kinetic energy. So if these are all held at the same temperature, the average kinetic energy is the same, but what changes is their distribution of speeds. So we see that we have helium, neon, argon, and xenon. Those are the choices, and xenon is the heaviest, So most of xenon's molecules are concentrated at a very low speed. Helium is the lightest, which means that they have, even though they have the same kinetic energy, on average, the most prevalent speed is faster than the most prevalent speed for a much heavier gas. And since the average is faster speed, okay, that would be that root mean square velocity, for those of you who remember that term, that average speed is higher, that means that the distribution is a flatter curve. Even though the area under the curve is the same, this curve is flatter because of the fact that there are faster speeds available to the helium, even at the same average kinetic energy. Now, if we're talking about the same gas at two different temperatures, we know that temperature measures the average kinetic energy and that this influences the speed. But if we have the same number of molecules and we have the same gas, but we change the temperature, the distribution of speeds changes, because we said that at a higher temperature, the speed that is most prevalent will increase. At a lower temperature, the speed or velocity that is prevalent will decrease. Because the area under the curve tells us the amount of molecules, we wind up flattening the curve and distributing those molecules over a greater amount of speeds, or a greater range of speeds, as we increase the temperature. We also know that activation energy is the minimum amount of kinetic energy that molecules need to have upon collision to cause an effective collision, which would lead to a reaction. And since molecules in a sample have differing kinetic energies, not all molecules will have enough kinetic energy to meet the activation energy barrier. So if this is the most prevalent speed or most prevalent kinetic energy, and this is the amount of kinetic energy that the molecules must have in order to in order to collide effectively to cause a reaction, only a certain number of molecules will possess that amount of kinetic energy. We can add more molecules to the molecules that have enough kinetic energy in two ways. The first way is to add a catalyst. When we add a catalyst, remember, the reaction will have a new pathway that it takes, a new mechanism that it takes, and this new mechanism will require less activation energy. By requiring less activation energy, that means that this new lower activation energy will now include more molecules than were included before. These molecules now that have at least this much kinetic energy will now possess enough energy to meet that activation energy barrier, so that when they collide, that collision, if it has the right orientation, can lead to a reaction. It can be a successful collision that will lead to the particles reacting with each other. So adding a catalyst moves this activation energy line to a lower amount of energy, including more molecules that have enough energy to react. We said that this was like lowering the standards. So if this is how much or how high your grades need to be to qualify for something, in order to get more people to qualify, we can lower the standards. We can make it so that the standards are requiring a lower grade, now including more students to make whatever program or be accepted into whatever program they were trying to get into. So activation energy is like lowering the standards. It lowers adding a catalyst is like lowering the standards. By lowering the requirement of activation energy, we now include more molecules that can collide with a successful collision based on activation energy. Don't forget that we still do need to have proper orientation according to the collision theory, but at least if there are more molecules with enough energy, part of that will be met when a catalyst is added. We can also see here that if at that original temperature, this red area or the diagonal lines show us how many molecules or the fraction of the molecules that would have enough activation energy at a lower temperature, another way to increase the number of molecules that are able to have an effective collision based on energy is to increase the temperature. Remember that by increasing the temperature, we push more of those molecules over to a higher over to a higher kinetic energy individually. And that means that if this line here is the activation energy, now we've actually made it so that these additional molecules with the vertical lines here, which are shown in blue, are also able to react once we increase that temperature. Hopefully that was helpful. Again, this is Mrs. T from Mrs. T's Chem Talk Extra Help Coronavirus Edition. Hopefully that helped. If you want to just send me a message on Remind or send me an email from my students and let me know if you need any more help with that at any point. I hope that everyone is healthy and safe, and I really hope to see everybody again in school very soon.